Hi everyone, my name is Tao. I'm from Carnegie School of Computing, University of Utah. Today I will present our paper, Marginal-Certainty-aware Fair Ranking Algorithm. Today's presentation are going to be 4 parts: the introduction, our method, experiment, and our final conclusion. First, let me give you some motivation of what we are going to solve in this paper. So first of all, ranking system is a two-sided market with users on one side and providers on the other side. In user side, users have information leads, so it's important for us to put more relevant items on top ranks. And we refer this objective as the effectiveness. And on the item provider side, item provider can provide items for users to satisfy their information needs. And in return, the item providers can get revenues. And so it's important for us to create a fair ranking environment. And we refer this objective as fairness. So generally, there are 2 objectives we are going to optimize during this in our work: the effectiveness and the fairness. The first question is why item providers can be unfairly treated. The answer is the mismatch between relevance distribution and exposure distribution. For example, here we can see an exposure heat map in the left. And we can see that usually the user are going to put more attention on top ranks instead of lower ranks. However, the item's relevance didn't necessarily follow this kind of distribution. For example, here I give you a toy example. Here are 3 items. They have very close relevance, but here there is a rank list that A is the first, C is the last, due to their relevance. However, the C is very unfairly treated because C is have very similar relevance, but C get very few exposure from users. So generally here the fairness issues come from the bias in users' attention. So here I give you some definition of ranking fairness. Generally, the principle is that items of similar relevance should be treated with similar exposure. That is, it follows a proportional relationship. And the formal definition is that we can, for every pair of items, we let their disparity between exposure and the relevance to define the unfairness. And the fairness is just a minus unfairness. And here I will introduce how does existing works usually to solve this kind of unfair ranking problem and their problem. And existing algorithm usually first giving a collection of items, and they usually first estimate their relevance. And based on the cumulative exposure, and they will decide which one is unfairly treated. And in later rank list, we will boost those unfairly treated items in future ranking. However, most existing ranking algorithms usually ignore that the relevance estimation contains uncertainty. Here, uncertainty means variance. Since the relevance estimation is usually not perfect and contains uncertainty, which can make existing fair ranking algorithm fail. Here we will introduce our method, the MC fair. First, just let me remind you that ranking system is a two-sided market with users on one side and item providers on the other side. That means we need to optimize effectiveness and fairness at the same time. And in our work, we add additional term, the third term, that is the uncertainty part. We want to reject the uncertainty here. And further, we found that at time step T, it's equivalent to maximize the incremental objective. And furthermore, we just do a first order approximation. That is, we use the first order partial gradient to multiply the the incremental exposure, and the incremental objective can be formulated as the sum of product between the partial gradient and the exposure. The delta exposure, that means the incremental objective, the incremental exposure at the next rank list. And we further propose that we should directly use the partial gradient as a ranking score to rank items. The reason we can refer to the rearrangement inequality, that is given x1, x2, and xn, and y1, y2, and yn. The maximal sum of product can be achieved when we have ordered x and y and multiply them together. And here is a small example. Since the objective is the sum of product between partial gradient and the exposure, so generally to make their sum of product the maximal one, we need to make the greatest gradient to have the highest exposure. That means we should let the gradient as the ranking score. And here let me see. Here this part is what we defined as the marginal certainty. It is it can be an additional score besides the effectiveness gradient and the fairness gradient. This score can help us to do some exploration to help us to have a more accurate estimation of relevance. And finally, I will introduce the experimental results. We do semi-synthetic experiments on MQ 2008 and EastLS datasets. Those are the learning to rank datasets. And since we don't have access to live ranking system, we synthesize clicks on those two datasets. And we have a wide range of fair ranking algorithms to compare with. And here is the ranking results. The x-axis is the unfairness. The y-axis is the ranking performance, the NDCG, the cumulative NDCG. And we found that given the same unfairness tolerance, our algorithm can have better ranking performance. Our method is the MC field here. And besides, we also do an operation study. And I want to remind you that there are three parts: the effectiveness part, fairness part, and uncertainty part. So there are 7 combinations when we do an ablation study. And the ablation results forms a very interesting loops. And we found that only when we consider all 3 parts, we can get the best performance. And finally, here comes our conclusion. Our MC field is a lower uncertainty-aware fair ranking algorithm, and it uses partial gradient directly as a ranking score. And all 3 parts of MC field are essential. And we found that most existing fair ranking algorithms can be unreliable when relevance estimation contains uncertainty. So thanks.